Today's lesson is going to be on Lesson 13, Graphing Systems of Inequalities. Let's talk about why it's important to learn how to solve a system of linear inequalities. Factory machines often have settings that engineers have to adjust to achieve desired production results. The machine inputs and desired outputs can be thought of as a system of inequalities, where the sweet spot is represented by the solution to a system of linear inequalities. There's an entire branch of mathematics that studies this, and it's called linear programming. When I worked as a production engineer at Motorola, this was primarily our duties, is to figure out how we can minimize scrap, increase tool uptime, increase production speed while avoiding certain scrap categories, and that always came down to solving a system of linear inequalities to find that sweet spot, dialing in the machine. So let's talk about what exactly a system of linear inequalities is. All right, a set of two or more linear inequalities have the same variable, such as x or y, and again, they won't be raised to any power. No x squareds, no y squareds, no y cubes. All right, and the solution to the system of inequalities is often an infinite set of points that can be represented graphically by shading. So what do I mean by that? All right, let's take a look at this system of inequalities. We got x minus 2y is greater than or equal to 1, and y is less than negative 3x plus 3. When graphing a system of inequalities, it's important that you get the inequality into slope-intercept form. All right. So when we take a look at the red line, we already have it in slope-intercept form. Y is less than negative 3x plus 3. So in order to graph this, I went up to the y-intercept, which is positive 3, put a point, and then because the slope was negative 3, I counted down 3 and to the right 1 to get another point on the line. Then I had to decide if the line would be solid or dashed. All right, and when we have less than or greater than, the line's just going to be dashed. So in this case, I connected those 2 points with a dashed line. After we connect the 2 points with a dashed line, we have to decide where's the shading going to be. And whenever we're deciding when to shade, I always want you to think about it in terms of up and down, or above and below. Never think of it as left or right unless you're dealing with an inequality of a vertical line. All right? So we have this equation written as y in terms of something else, and y is the vertical axis, up and down. So in this case, when we have less than, right, or less than or equal to, we're going to shade it below. Less than, below. Makes sense. So I kind of go to where I have the y-intercept, the point on the y-intercept, and I say to myself, it should be shaded below this point. So everything below should be shaded. All right, I saw many responses where students think of it as left or right, but that's going to mess you up, because if the slope of the line is positive or the slope of the line is negative, that would change the side that you shaded it on. So instead of thinking about left or right, think about it in terms of above and below. So here I lightly shade in. If you're doing this by hand, I would lightly shade in below the line. Now I need to graph the blue inequality. X minus 2y is greater than or equal to 1. In order to do this, I'm first going to get it into slope-intercept form. All right, so I'm going to take x minus 2y. I want to get the y by itself. Right, so I need to get rid of this x term. I need to push it to the other side of the inequality using inverse operations. So after I subtract x from both sides, I'm left with negative 2y is greater than or equal to negative x plus 1. We almost have y by itself. The last thing we need to do is divide by, in this case, negative 2. So we divide everything by negative 2, and I get that y is less than or equal to, we can think of this as 1/2 x minus a half. Now if you're careful and you've noticed, the inequality symbol has switched. It's become from greater than or equal to less than or equal to. That is not a mistake. Right? You recall that when you are dividing by a negative or multiplying by a negative with an inequality, right, when your action is to multiply or divide both sides by a negative, you have to flip the direction of the inequality symbol. And that's why it's important to get the inequality into slope-intercept form so that you know what direction you have to shade. Alright, so as always, I'm going to go ahead and I'm going to plot this point, the y-intercept, which happens to be negative 1/2. So I'd come down at negative 1/2, roughly here, and I'd put a point. Then I'm going to use my slope of 1/2, right? 1/2. We don't see the 1 there, but it's always implied. So I have a point at negative 1/2, then I'm going to go up 1 and to the right 2 and put another point. So let's go ahead and do that. Right, so there was my point at negative 1/2. Then I went up 1, so that would have put me at here at 1/2, positive 1/2, then over 2 and put another point. Then I noticed that the line was less than or equal to. Remember, when it has the or equal to, it's always going to be a solid line. So we graph the solid line. Then I have to decide where to shade. Less than or equal to, as always, means below. So I'm going to shade below. Look what happens when we shaded below. There's a region in here where the shading overlapped. That is the solution to a system of inequalities. And it's an infinite set of points. That means that any point that I picked in here, like say this point right here at -2, -4, if I plug them into the original equalities, I would get a true statement, When we were talking about our linear program and dialing in the machines, usually you have a whole system of linear inequalities, multiple ones, and where the corners are represent some kind of optimal point, whether it's maximizing profit or speed or reduction of scrap. Let's do another example. Let's graph this system of linear inequalities. Well, the nice thing is we already have the blue linear inequality in slope-intercept form. So I'm just going to go ahead and plot a point at 1 and go up 3 to the right 1 and get another point. Since it is or equal to, we know it's going to be a solid line. And then we have to decide where to shade it. Greater than means above. Kind of makes sense, right? It's greater, it's above. So I shade above. And again, to decide where that is, I go put my little pencil on the y-intercept and I say it's above. Should be shaded above this point. Okay, so all this point. Let's go ahead and graph the other one. But before we can do that, we have to get it into our slope-intercept form. Notice this time I just divided by +3, so I didn't switch the inequality, right? It's only when you multiply or divide by a negative that you switch it. Alright, so we've had plenty of practice graphing lines now. We graph it just like we would if this were an equal sign at 3, and then we use our slope of -2, meaning I go down 2 to the right 1 and plot another point. If you need help graphing lines, contact me via email or messenger and I'll help you do that. Because obviously that's a necessary first step in order to graph the linear inequalities. Now since this was simply less than, I made it a dashed line. Right? It's dashed because we don't want to include the solutions that are on that line itself. Right? Just the ones that are below it in this case. So I'm going to go ahead and shade below. And did you guys see where the shading overlapped? Right, it overlapped there. So yellow and blue made green. This green region is what we would call the solution region. And it's infinitely many points, right? It goes on forever in this negative direction in this case. So one last time, let's graph this system. One of the equations is already in slope-intercept form. I plot at -1. I go down 2 and to the right 1 to get another point. And also, you could also think about it as -2 over +1, or you could think of it as +2 over -1. +2 would mean go up 2, and then -1 would to the left 1. Not this -1, but right here, -2 over 1, the slope. It doesn't matter which sign we put the negative on, the numerator or the denominator. So that's how you can get these other points as well if you ever needed to, if you run out on a graph. of space. All right, so we have it that it's greater than or equal to, so we shade it above. Right, greater than or equal to, shaded above. So I would lightly shade in this with my pencil, and then I'd go about plotting the other line. So I have to divide everything by -4. And I really want to show you guys that when you divide by a negative, this is the most common mistake, that you have to reverse the direction of that inequality symbol. Right, so it's no longer going to be greater than or equal to when we do it. It's going to become less than or equal to. So pay attention. You only do that when you have to divide by a negative. Usually it's divide, but it's also thought of as multiply. Right? So I go to -4, and I would plot a point, and then I'd use my slope. And then because we have the or equal, it's a solid line. Less than or equal to. So I go to my point and I say the shading should be below here. So I would shade everything below the red line, and that results in this region being overlapped, right? Overlapping solutions. Before I go on and talk about this problem, let me go back to this, because you have a couple of examples in your projects that I want to discuss. When can you have a system of inequalities that has no solution? All right. So I'm going to go ahead and back up and show you. So right now, just ignore these inequalities here. I just want to use the graph and show you what happens when you have no solutions. If I can get my pen. All right, so I saw many discussion boards where a lot of students had the first part of it right. They said, hey, if we have parallel lines, that's when we can get no solution. And they're close. That's kind of like the answer when we have just a system of linear equations, right? If the lines never cross, then there can't be any solution. I know these aren't straight lines, but imagine that they were. Well, when we have a system of linear inequalities, remember there's always shading somewhere. It's either shaded above or below. So the only time that we get no solutions to a system of inequalities is one, yes, it's a requirement that we have parallel lines, and then two, one of them needs to be shaded above like this, and the other one shaded below like this, so that there's no overlap. All right, so when there's no overlap, that's when we get no solutions. But it is possible to have parallel lines and still have solutions. So for example, if I have a parallel line here, and I have this parallel line here, and I have this inequality happens to be shaded below, so anything below, and this inequality that's on the bottom line happened to be shaded above, you would see that they would have overlapping in between them. Alright, so in this particular case, we would have two linear inequalities that have the same slope that results in solutions. Let's see, let's actually do this one. So this line right here, this horizontal line, would be the equation y less than, since I have a solid line, equal to the number 3. So anything below 3 shaded. And this line right here is the line y greater than or equal to, in my case, 1. So I shaded everything above 1 and the shading overlapped in between. So that resulted in solutions. Now if I went ahead and I flopped this, if I said make this one greater than or equal to, and this one less than or equal to, then this shading would have been above, and this shading would have been below, and then there would have been no solutions. So let me just quickly move to the next slide. All right, so let's talk about an application. Solving a word problem involving linear inequalities. All right, Sally is at the candy store and has at most $8 to spend. She wants to buy cookies and chocolate bars. Her parents allowed her to buy at most a total of 6 cookies and/or chocolate bars. The cookies cost $1 a piece, and the chocolate bars cost $2 a piece. All right, write a system of linear inequalities that can be used to model the amount of cookies and chocolate that Sally can purchase. All right, we're going to go ahead and define our variables. So we need a variable to represent the number of cookies, all right, and we need another variable to represent the number of chocolate bars, all right. So I'm going to go ahead and let x be cookies and y be chocolate bars. And we see here that she is allowed to have at most a total of 6 cookies. At most is the key word here. All right, so when I say at most, I mean, to me that implies, right, that I can have 6 cookies and or chocolate bars, but I can't have any more than that. But I can have less than that. All right, so when I see the word at most, I know that means less than or equal to. This one right there is going to be telling me that it's less than or equal to. Now I know that also this line here where it says a total of means the sum of something, a total sum. All right, so then in this case that implies to me that if I take the number, because remember x is representing the number of cookies and y is representing the number of chocolate bars, if I total them together, meaning add them together, that can be at most, which means less than or equal to 6. All right, so there's one equation that we wrote. Now I need another equation because not only do we have a constraint, right, on how many total number of cookies and chocolate bars we can buy, we also have a constraint on the number of dollars we have. We have at most $8 to spend, right? So I'm going to write an equation that models the cost. All right? And the reason why we put 1x, right, is because the cookies cost $1. So if x is representing the number of cookies, and let's say I buy 3 cookies, then I would buy 1 times 3, or that would be $3. So remember, this equation here is representing the cost. So it's $1 per cookie, and I add that to, right, $2 for every chocolate bar that I buy. And that can be, in this case, at most $8. And again, at most means 8 or less. It can be 8, but it can't be any more than 8, and it can be less than, so it's less than or equal to. All right, some of the key words that you should be looking for are words like, obviously, this one, at most. If something was greater than or equal to, the word associated with this is at least. Right? So look for these keywords when you're solving a word problem to determine which inequality to use. Okay, so now we have 2 inequalities. All right, and we're going to get them both in slope-intercept form, just like we did in the previous problems. All right, so we didn't have to divide by any negatives here, so the sign stayed the same. All right, now we have our 2 inequalities. I'm going to go ahead now and graph them. So this was our first inequality, and here's our second inequality. So I'm going to go ahead and plot this y-intercept at 6. Then I'm going to use the slope of -1. So that means I go down 1 and to the right 1. Put another point. Then go ahead and connect those with, in this case, look, it's going to be a solid line. All right, so it's a solid line. Now we decide where the shading needs to be. Well, it says that it's less than or equal to. Less than means below. So there's the region that we shade. Okay. Now let's go ahead and graph our second inequality. I plot the point at positive 4. That's this point, the y-intercept. Then we have negative x over 2. That's really a slope of negative 1 over 2x. That means the same thing as this. Okay. So that means I should go down 1 and to the right 2 to get to another point. So I'm going to go down 1 to the right 2, and we'll put a point right there. All right. We'll go ahead and connect that with a line. Again, it was a solid line because we have the or equal. And also we have less than or equal to, so I'm going to shade this one below. Alright, so we go ahead and shade it below. And then look at all this entire region here that overlapped. Right, the solution is where they overlapped. However, we got to think back to the context of this problem. So in a normal setting, when I was just graphing these two inequalities, this would be the solution region, right? And anything in there is a solution. However, in this case, we're talking about chocolate bars and, chocolate bars and cookies. All right, so I want you to think of this x as representing the number of cookies, and the y is representing the number of chocolate bars. Does this solution right back here make sense? Because that would imply that I have negative 3 cookies. All right? So here we're saying, hey, Sally can't buy negative amounts of cookies or negative amounts of chocolate bars. So really the solution is just the positive part of that answer, this region here, just in quadrant 1. So there's our solution, because in the context of this problem, negative values don't make sense. A few examples: you have to graph the inequalities and then describe the region that it creates. Classify the figure created by the solution region is usually the wording they use. When we have an inequality that's just x less than or greater than some number, that means you go over on the x-axis to that number and it's a vertical line. If I have y, like you saw, equal to some number, then I go to that number on y and I make a horizontal line. In this case, it looks like we have a vertical line at 6 on the x-axis. Alright, so I'm going to go ahead and graph that one first. And it's going to be a solid line due to the fact that it's or equal to. In fact, all of these are going to be solid lines. Right? So in this case, this is the only one where it's hard to say shade below, right? But below means less on the x-axis, means less. So that would mean all to the left in this case, and that's the only time you'll hear me say left or right as versus above or below, right, when we have a vertical line. So in this case, we're shading it to the left here. We're shading it below 6. So you might think about it like that. I'm going to go ahead and graph the other two. And again, if you need help graphing lines, because all we're doing is graphing it the exact same way we'd graph a line with using the slope and the y-intercept. But then all we have to decide is, should it be solid or dashed, and where the shading should be. So here's our line here, and we're going to shade it below. Alright, so now pay attention which parts have overlapped so far, right? All this region in the blue in this case has overlapped so far. Now I got one more inequality to graph, this purple one, so I'm going to go up to 4 on the y-axis, because that's the y-intercept. I'm going to go down 2 and to the right 1 and plot another point. And again, we're going to make another solid line. Shading, in this case, above. So think about it. Here's the y-intercept. I'm going to shade it above. That means this region up here. And when I finally do that, you're going to notice that that region right there that is now blinking was the one where they all three overlapped. Alright, so this is the solution region. And if we want to classify the figure, we would call that a triangle. Okay, so the region created by the system of linear inequalities in this case is a triangle. Let's do another one. Alright, so we're going to graph the vertical line. X is less than 5. I go to 5. I'm going to draw a dashed line this time, right? Because it's just less than. And it's shaded less, so to the left in this case. And then we're going to quickly go ahead and graph our other line. So we're going to plot one at -4. And then remember, we're going to go up 2 and to the right 1 and put another point. And this time it's going to be a solid line. And we're going to shade it below. That means down here below that region. Alright, so now here's where we have a horizontal line. Y is greater than or equal to -4. So we're going to go to -4 and we're going to draw a horizontal line. And in this particular case, we're going to shade above. Like so. One left. Y is less than 3. Alright, so that is a dashed line at 3. And the shading is below. Alright, so in this example here, notice that even I made a mistake here, right? This simply says y is less than 3. However, I hope some of you picked it up, right? I have graphed a solid line here, right? That is incorrect. It should be a dashed line there. And we are going to shade it below. Alright, and notice that all 4, where the shading of all 4 regions overlapped, is in this area right here. So now if I have to classify that figure, well, I have 2 parallel bases in this 4-sided figure, and technically this figure is called a trapezoid. So I'd classify that as a trapezoid. Alright, so now I want you to go ahead, pause the video, and take a look at this question. Once you think you have the answer to number 1, right, go ahead and open up the asynchronous questions for session 3. Submit them in your Google form and turn it in as always. If you have any questions, please feel free to email me or message me or call me.